Hey everybody, welcome back. This is CHEM300 and we're continuing our discussion on chapter 10 with talking about resonance structures in this section. So resonance is when you can have equivalent Lewis structures for the same molecule. So our goal in this section is to explain the concept of resonance and how it works within molecules. So resonance is the use of two or more Lewis structures to represent the covalent bonding in a molecule. So this happens when two structures are equivalent, except for the placement of some of the electrons. So the atoms are connected in the same way, the same connectivity. The only difference is the placement of some of the electrons. And so when two structures are equivalent, except for the placement of some pairs of electrons, those are resonance structures. So resonance structures occur when electrons can be shifted in a molecule, usually by moving a double bond or lone pairs around, without changing how the atoms are connected. So this is the molecule ozone, O3, down at the bottom here. And there's two ways to draw it, right? You might draw it like this. It has 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons placed on it. Everything has a full octet. And then the person next to you might draw it like this, right? They might do it all the same, except for put the double bond over here instead of on the left. Still has 18 electrons. All the atoms still have full octets. So they're identical, except for the placement of some of the electrons. Here we have a double bond on the left, and here we have a double bond on the right. And so these two structures are called resonance structures. They're two equivalent Lewis structures, but the electrons are in slightly different places, as shown by this double bond either being on the left or being on the right. And so they're typically drawn with an arrow between them, showing that they're equivalent. And it used to be thought that these electrons were actually kind of swinging back and forth, like they'd be here and then they'd swing over here and then they'd swing back, which is why that double-headed arrow was used to show like these are shifting back and forth between the two of them. But we now know that that's not actually true. What happens is that these electrons, instead of shifting back and forth, they kind of just average out across this whole space. And so when we draw kind of the final resonance structure, we draw the average of the other resonance structures. And we show that it's the final or average resonance by using these dashed lines. The dashed lines show that this double bond can be in either location. And so we draw those dashed lines to show it's not fully on the left and it's not fully on the right. It's kind of shared all the way across here. The way that we were able to figure this out is because single bonds are longer than double bonds. So if we had the two separate structures just swinging back and forth between one from the other, we'd expect this to be a shorter bond length and this to be longer. Double bonds are shorter than single bonds. So the distance between these two oxygens would be less than the distance between these two. Double bonds are shorter than single bonds because double bonds have more electrons. There's 4 electrons shared between these two atoms. And so they get pulled closer together by sharing more electrons. So if the electrons are really just like swinging back and forth from one structure to the other, like flip-flopping back and forth, then we'd be able to measure that sometimes the bond is shorter on this side and longer on this side, and in this structure it'd be longer, and this way it'd be shorter. So if we took a collection of ozone molecules, we'd find some that had the left side was shorter than the right, and some that had the right side was shorter than the left. But instead, when we measured the bond lengths in ozone, we found that they had the same bond length. So it's not that these two electrons are flipping back and forth, making one side longer and one side shorter, and they're just changing, flipping around. It's that the electrons are actually spread out between all of these locations, giving the same bond lengths between all of the oxygens. Versus if it was one double bond and one single bond, the double bond would be shorter. A shorter distance between these two oxygens can be measured versus a longer distance between these two. So that's how we figured out that resonance was happening, that we get these resonance structures, these equivalent structures, but in reality, they kind of average out so that the two bonds that the electrons are shared across end up with equal bond lengths. And these bond lengths were a little bit longer than a double bond and a little bit shorter than a single bond, kind of like a hybrid between a double and a single bond. So let's do some practice. You'll get some of these in the homework where you draw a Lewis structure for a compound, and then it asks you to draw any resonance structures if applicable. So let's practice with the nitrite ion. So you always start out the same. You want to count your valence electrons. So nitrogen has 5, oxygen has 6. We have 2 of those equals 12. And then we have a -1 charge. So we have to add another electron in. So when we add that up, 5 plus 12 plus 1, we get 18 electrons total. So now we're ready to draw it. Nitrogen goes in the middle. It's got to be connected to each oxygen with 1 bond to keep it all together. So 18, and we used up 4 electrons in bonds. So we have 12 electrons left. Oh, 14 electrons left. See if I can do simple math in my head today. Okay, so let's put those 14 on. We want to fill octets working our way from the outside in. So we're going to put 6 around this oxygen to get 8 total around it. Let's put 6 around this one to get 8. So that's 12 non-bonding. So we have 2 electrons left. So I'm going to put them on nitrogen. Now we don't have any electrons left. So now we have to check to see if everything has a full octet or as close to a full octet as it can get. Each of our oxygens have full octets, but if we check nitrogen, it only has 6 electrons around it, 2, 4, 6. So to fill up nitrogen, we can take 2 electrons from oxygen and turn it into a double bond. And if we do that, and now we count up the electrons around nitrogen, we have 2, 4, 6, 8. So now nitrogen also has a full octet. So this is a good final structure. We could check formal charges if we wanted to, just for a little bit more practice with that. We check the formal charge on this oxygen. It came in with 6. It has 4 dots and 2 bonds, so it has a formal charge of 0. We check on nitrogen. It came in with 5. It has 2 dots and 3 lines, so it has a formal charge of 0. And this oxygen came in with 6 electrons. It has 6 dots and 1 line, so it has a formal charge of -1, which is fine because our formal charges have to add up to the charge on the molecule. And this is a polyatomic ion with a charge of -1. So we expect the formal charges to add up to -1, and they do. So this is a fine structure, but it's not the only structure. I randomly chose to take 2 electrons from the leftmost oxygen and turn it into a double bond, but I could have just as easily taken 2 electrons from the rightmost oxygen and turned that into a double bond. And so nitrite has resonance. We draw our arrow here. It could also be drawn going back to before I put the double bond in. I could just as easily put the double bond in on the right and make it right there. And so these are 2 resonance structures. They're the same except for the placement of the double bond where those electrons go. And so if we wanted to draw the average resonance structure, let's get rid of all this formal charge stuff. My eraser, there we go. All right, so we have these 2 resonance structures. The only difference is the placement of that double bond. It's just as easy to put it on the left as it is on the right. I don't have to switch the places of any of the atoms. All of them still end up with full octets. The overall formal charge, charges still add up to -1. So if I wanted to write the average resonance structure for this would be nitrogen, oxygen, oxygen, with dashed lines between. Make sure those show up as clearly dashed to show that this double bond could be on the left or it could be on the right. And because this is an ion, when you finish drawing the structure, you always put the brackets with the charge. Like so. So be aware, this happens a lot when you're placing electrons from an atom on the edge to make a double bond to give the central atom a full octet. It's common to have resonance structures when you do that because it's just as easy to move electrons from, say, the leftmost oxygen to make a double bond with nitrogen as it is from the leftmost oxygen. So when you see that situation where you're moving electrons from lone pairs to make double bonds around the central atom, check for resonance. That's a common situation when there can be resonance. Okay, let's do another one. Let's draw the structure for acetate, CH3COO-, and any resonance structures. So this is another ion, so we're going to have to account for the charge when we draw the structures. So we always start with counting the valence electrons. So carbon has 4, hydrogen has 1, we have 3 of those. Oops, we've got 2 carbons. My math is just off today. And oxygen has 6, and we have 2 of those. And we have a -1 charge. So we need to include an additional electron. So when we add this up, 12 plus 8 is 20, plus 4, 24 electrons total. So let's start drawing it. In this case, the formula was written to give us a clue about how to draw it. We want to put a carbon with 3 hydrogens around it, connected to another carbon, which is connected to 2 oxygens. So when we start drawing this, we kind of follow the formula left to right. A carbon with 3 hydrogens around it, connected to another carbon, this one right here, which is connected to 2 oxygens. So there's our basic structure with everything connected with a single bond to hold it together. So we used up 2, 4, 6, 8, 10, 12 electrons and bonds. So we have 12 electrons left. So we need to check for full octets. Each hydrogen has a full duet because it has 1 bond, which is 2 electrons, so we don't have to add anything over here. This carbon already has 4 bonds around it, which is 8 electrons, so it's full. We don't have to add anything here. Our oxygens don't have full octets, so we're going to add electrons around our oxygens to get them to full octets. So now they both have full octets, and I used up my remaining 12 electrons. But if I'm checking octets now, carbon right here, it only has 2, 4, 6 electrons around it. So I'm going to have to do some shifting. And this is when resonance comes into play. Anytime I'm shifting electrons, and it's going to happen from one of these oxygens, I'm going to turn their lone pair of electrons into a double bond. I have 2 oxygens right now that are equivalent, right? This top one and the side one. There's really no difference between the 2 of them. I could take 2 electrons from the top one and move them down to make a double bond to give carbon a full octet. Or I could just as easily take 2 electrons from this one on the side to make the double bond. And because they're equivalent, the only thing that's different would be which oxygen I pull the electrons from, but I'm not changing the structure, like how the atoms are connected. That's going to make 2 resonance structures. So let's do the first one. I'm going to take electrons here and move them down to make a double bond. That gives carbon 2, 4, 6, 8 electrons, and this oxygen still ends up with a full octet. I could have just as easily pulled the electrons from the other oxygen. And so that's going to be my second resonance structure if I had done it the other way. So everything else is the same. We have your C with 3 carbons, carbon. Here's our structure. And now instead of pulling my electrons from the top oxygen to make the double bond, I'm going to pull them from the side oxygen. So I'm going to pull these two and make a double bond here. Get rid of those. There. We check carbon, it still has a full octet, 2, 4, 6, 8. Each oxygen has a full octet. So these are equivalent structures. The only difference is the location of those electrons that make up that double bond. So if we wanted to draw the overall average structure, we'd have our carbon with 3 hydrogens. So I'm going to draw small because that part's not changing. Carbon, oxygen, oxygen. And then we draw a dotted line to show the 2 spots where that double bond could be, like so. The average. And because this is an ion, has a -1 charge, your final structures need to go in brackets with a negative charge. These ones too. So we have 2 resonance structures, and then from those 2 resonance structures, we can make the average structure shown here. Okay, so key things to look for when drawing resonance is after you've placed all of your electrons, when you have to take lone pairs and turn them into double bonds to fill octets on a central atom, if there's 2 places you could possibly pull the electrons from to make that double bond, you have to draw both of those possibilities as resonance structures because it's the same molecule. The only difference is where you're pulling electrons from to make that double bond. So we showed 2 examples of that with nitrite ion NO2 minus, and as well as with the acetate ion CH3COO minus. Let's do one more. This is from the homework. Draw the structure for hydroxide OH minus and any resonance structures. So see if you can do this one on your own. You always want to start by counting the valence electrons. So we have oxygen, it has 6. We have 1 of those. We have hydrogen, it has 1. We have 1 of those. We have a -1 charge. So that's going to add an electron. So we get 8 electrons total. Now let's draw. So we only have 2 atoms, so there's no central atom. O connected to H. We use 2 electrons in the bond, which means we have 6 electrons left. So hydrogen has a full duet, it doesn't need any more, so we're going to fill around oxygen. So now we don't have any electrons left. Put the brackets around it because it's an ion with a negative charge. And now, is there any way we could draw resonance structures for this? Do we have any spots we could make double bonds, move or shift electrons around to fill octets or duets if needed? And the answer on this one is no. There's no possible, no resonance, because there's no way we could shift electrons around in this. Hydrogen only needs 2 electrons to have a full duet. So we can't have a double bond to hydrogen because can't double bond to H. Hydrogen is filled up with 2 electrons. So we can't take 2 electrons from here and make a resonance structure. It's impossible. Hydrogen can't fit that many, so it wouldn't be an equivalent structure. So for this one, and you'll get a couple of these in the homework, you draw them out, and then it asks you to draw resonance structures if applicable or if possible. And there's going to be some cases where you can draw resonance. And then there's going to be some of these cases where you draw the structure and there's no way to shift electrons to make a double or a triple bond. Oftentimes because it's like next to hydrogen or next to chlorine or one of the halogens, which only make 1 bond. And then, so in that case, there's no resonance possible. So just be aware of that. There's some that are a little bit tricky where it asks you to draw structures and then resonance if applicable. And there's going to be some where there's just no resonance. And so you only draw the main structure and then just put no resonance. Okay, so that's the end of part 2. We're going to continue part 3 next time, talking about electronegativity and why oil and water don't mix, as well as the 3D structures of molecules. I'll see you then. Thanks, everybody.